All right, howdy folks. Welcome back to Professor Carbon. In this video, what we're going to do is go over an arrow pushing mechanism for the formation of a lactone using the Yamaguchi reagent. And so that's the reagent shown here. And the reason we like using the Yamaguchi reagent is often we have to make an ester or a lactone in a very complicated molecule, and sometimes it's a disfavored ring to form. And so it becomes quite challenging to do that. And most of the methods that we've usually talk about in the Organic 1 and Organic Chemist 2 course have very strong acids associated with them. They're quite reactive. So things like the Fischer esterification usually use concentrated sulfuric acid in an alcohol. That's usually not compatible with really complicated molecules. Other conditions like thionyl chloride to make an acid chloride require the formation of HCl, and typically that HCl is not buffered. So again, it's quite acidic. And so if you have to form a lactone or ester late in the synthesis of a very complicated molecule with a lot of sensitive functional groups, you start to run out of ways to do that. And so the Yamaguchi is one way which that can be done. And so this is an example of a very complicated molecule shown here, where this was the case. And there's one ester functional group smack dab in the middle of this molecule that represents a lactone. And if you follow from here all the way around, it comes all the way back to an alcohol. And so what needed to happen for this molecule is a very long chain, and then it had to wrap back onto itself. And that turns out to be a complicated reaction. For those of you that want to read more about the complexities of that kind of reaction, I would encourage you to go read things like macro-lactonization methods. And it turns out there are a lot of them. One of the most famous is the Yamaguchi reagent. Okay, so this is an arrow pushing mechanism where we should be able to take this kind of squiggle thing and make a lactone. And so we've seen that this should be the bond that you're going to form. And instead of trying to draw something that's as complicated as this molecule, I'm just going to simplify everything that's not important as this kind of horseshoe shape here. So as with all of our videos, please now take a minute, pause this video, and I encourage you to work through this reaction all on your own. Okay, come on back through. Hopefully you have a good idea of the mechanism. Maybe you had an opportunity to, search the Yamaguchi reagent on Wikipedia or organicchemistryportal.com in the meantime. And what I would encourage you to do is to look those up after the fact if you haven't yet used those resources. The great thing about the internet is that it's covered with all sorts of wonderful help in organic chemistry, and hopefully you're taking advantage of these videos as well as a number of the other web pages that are out there. Okay, so the Yamaguchi reagent, if we notice, is an acid chloride here. And so the way that this is going to work is we're actually going to go through an anhydride intermediate. And so the nice thing about carboxylic acids is they're acidic, and the reagent that we're getting is with triethylamine here. And so we're going to use this to deprotonate that carboxylic acid. And I have my carboxylate anion here. And that carboxylate anion is a weak nucleophile. It's not a particularly strong nucleophile, but hopefully we remember that one way that you can make anhydrides is by having a carboxylate anion attack an acid chloride. And that's exactly what we're going to do here. So we'll move that around and have it attack. And so this would be the tetrahedral intermediate. Remember, all these acyl substitution reactions go through two steps: addition and then elimination. And so this would be the addition step, so it's time to do the elimination. And so we'll take that oxygen, kick it down, and kick chloride off as a leaving group. So let's put Cl minus there. And if we go back and balance our first step here, we would have kicked off TEAH plus. So let's just make that NH. And then we'd have our 3 ethyl arms here plus. And so overall, the byproducts of this reaction are going to be the chloride. So triethylammonium hydrochloride will be a dominant byproduct of this. And then we're going to have our anhydride. And so I'm just going to connect that arrow down to give myself a little bit of space. So we'll start here, O, O. Now, there are a couple of different mechanisms that you'll find online for the Yamaguchi esterification. A lot of them have the reagent DMAP in them, and DMAP stands for dimethylaminopyridine, which is this molecule shown here. And DMAP is a really good base, and it's also a really good nucleophile. And it's actually nucleophilic or basic on the N lone pair here. For those of you that are longtime followers of the channel, I actually have in the electrophilic aromatic substitution or in the fundamental reactivity lists, there's a whole video that talks about how you can tell that that's the basic nitrogen lone pair. And in short, it has to do with resonance. So these N lone pairs want to kick down, and they'll help make that nitrogen the more nucleophilic one. Okay, so the reason I mentioned DMAP is a lot of recipes have DMAP in them for the Yamaguchi. And it ends up just helping facilitate a second acyl substitution mechanism. For the practitioners of organic chemistry out there, I'm intentionally choosing to leave DMAP out of this video because it just complicates things a little bit more than it needs to. And so instead, we're just going to use TEA as a base for the overall process. All right, and so now we're going to have this lone pair attack because that's what alcohols do onto anhydrides. And so we'll move up our lone pair here. Oops. So that makes our tetrahedral intermediate again, and I've forgotten my pesky H+. And from here now, we can just swing this down and kick that piece off. So now we've made our lactone, and now we would have our carboxylate anion. And that's a great base then to pick up this H+ at the end of the mechanism. So that'll make one equivalent of trichlorobenzoic acid, but it'll also make our key lactone. And so that's what we want. Now, some of you might be asking about why this particular acid chloride. What's special about the Yamaguchi reagent that makes it uniquely able to do this particular reaction? And it turns out there's a couple of very important things about it. And so I wanted to talk that through here for a second. Most of the time when we have a benzoic acid, we know that it should want to be in the plane of the arene so that it can be conjugated with that system. And so let's just imagine a system like this one, para-methoxybenzoic acid. We can use that methoxy lone pair and delocalize them all the way up into that oxygen. And so this would be a resonance structure of para-methoxybenzoic acid. And of course, for things to be conjugated, they need to be flat so that all the p orbitals are lined up all the way down the system. And that's very important for conjugation, but it has a little bit of a complication when there's not one but two orthosubstituents. And so the Yamaguchi reagent is more complicated because of these chlorides. And so in the Yamaguchi system, if we actually have this acid, these chlorides are quite large, and they're going to start bumping into the flanking ortho groups. And because of that, that carbonyl is going to have to twist out of the plane. And so if I try to draw my benzene ring here on its side, I can put the chlorines kind of sticking out. And then that benzoic acid or acid chloride is going to kind of be twisted up. So this is kind of coming out at us. And then this chloride's kind of going back into the page. And this one's sticking straight up in the page. And so what that means is that it is kind of twisted out of the plane of conjugation because of these two ortho groups. And it turns out that's very important for a very specific reason. And if we think about the anhydride we had, and it doesn't matter what we have on the other side, and we have that pendant arm, or really any incoming nucleophile, that nucleophile could choose to attack this way, or it could choose to attack this way. So it could take pathway A or pathway B. And if it's random, then we have a problem. And the problem is that we're going to have a mixture of byproducts. And so what we really want to do is make pathway A favored so that we end up with the lactone, instead of pathway B favored, where we would just end up with an ester. And so this orientation here turns out to be very important because that nucleophile has to then attack the carbonyl carbon, and typically these carbonyl carbons are attacked by something that's called the Berge-Dunitz angle. And so if we put our sp3 system in a plane here, the incoming nucleophile kind of wants to come off the plane a little bit, and that particular angle, again, if you want to Wikipedia it or Google it all on its own, is called the Berge-Dunitz trajectory. And that Berge-Dunitz trajectory on the Yamaguchi system is right past this chlorine. And so it turns out these chlorines protect this system, and so they make that pathway B disfavored because the incoming nucleophile would have to go right past those chlorine atoms on either side. And so they're kind of protecting that attack on the way. The other thing that's important about the chlorines is we should hopefully recognize them as being weak electron withdrawing groups. And so they're helping make that carboxylate anion up here a better leaving group by withdrawing some electron density from that O minus. And so there's really a couple of things that make the trichloro pattern particularly important. One of which, again, is that it protects the incoming nucleophile and kind of pushes it towards the other way so that pathway B is favored. The other of which is that it's going to be inductively withdrawing, and so it's really going to help make it a better leaving group. Okay, so that sums up this video. I hope you've learned a little bit more about the Yamaguchi reagent, but also thought a little bit more critically about how nucleophiles actually attack carbonyls and how we can use that information to gain selectivity when we have two different pathways for which way the nucleophile could attack. If you're enjoying these videos, please do subscribe to the YouTube channel. We really appreciate the subscribers because they let us know that we're helping people learn organic chemistry, and that's really what this channel is all about. If you really want access to the notes, either before or after they're filled out, you can go ahead and click the Patreon link up above in the banner on the channel page. And if you subscribe on Patreon, you can get access to all the PDFs for these notes. So with that, thank you for listening. Please watch the next video and please tell your friends about us at Professor Carbon.